we can just as easily generalize this to two-dimensional collisions. If we have a collision where we're going to write our momentum beforehand, now we're going to designate x direction. It's going to be the mass of this cart multiplied by its velocity. The momentum beforehand in the y direction, neither of these two carts are moving in the y direction, so the momentum beforehand is going to be equal to 0. We do the same thing down here, where now we're looking at the momentum afterwards in the x direction. That must be equal to the momentum beforehand in the x direction, and the momentum afterwards in the y direction must also be equal to 0. That was the momentum beforehand. So what that's really saying is the momentum of the large cart right there, it's going to be cart A in the y direction, is simply going to be the negative of the momentum of cart B in the y direction. And we can do something similar in the x direction. So take a look at example 8.6, that's this one right here, and get a little bit more familiar with the two-dimensional version of this. So now that we're good talking about collisions, I need to talk about the two types of collisions we could have. And momentum is always going to be conserved in collisions. However, energy might not be. So I'm even going to go ahead and write that. Momentum is always conserved. Very important concept. So the first type of collision I want to talk about is going to be an elastic collision. You can consider two carts on an air track and they have springs in there coming together in a collision. All of the energy gets stored into the energy of the springs, and after the collision the balls, or the carts, bounce back, and they actually are going to have the same magnitude velocity, just simply opposite directions. In this case, momentum was conserved and energy was conserved as well. No energy was lost in that collision. However, in a collision that is inelastic, this type of collision is going to have momentum be conserved. However, it's going to lose some energy. Let me not misstate this and say that energy is destroyed. The energy actually is transformed into some other form other than the object's velocity. It may be, or more likely than not, two bodies, two automobiles for example, might be colliding, in which case metal is going to be bending, it's going to be heating up, there's going to be friction between the two various metals, so on and so forth. In that case, some of the energy goes into other forms, friction, heat, so on and such forth. In this type of collision, before and afterwards, the velocities are not going to be equal in magnitude and opposite in directions. And in fact, a very special type of inelastic collision is going to be a completely inelastic collision, where if I had some Velcro on these carts rather than springs, they're going to come together, they're going to collide, they're going to stick, and then afterwards they're going to be moving off at some velocity. Here we've kind of assumed that they're going to have the same mass, and this one has a larger velocity, so kind of intuitively you know it's going off in that direction. And we'll work a problem or two with completely inelastic collisions because they're fun and they're easy. So as I mentioned on the last slide, we can have inelastic collisions where things stick together, and cars are actually intended to have these collisions so that the car absorbs as much energy as possible. If I consider a collision, I'm going to be looking at the momentum before, I'm going to be looking at the momentum afterwards, and the momentum is always going to be conserved. I'm always going to say that the momentum beforehand is going to be equal to the momentum afterwards. If I look at the momentum beforehand, I'm going to have the mass of A and the velocity of A initially, so velocity of A, 1 being the initial state, and I'm going to add mass of B multiplied by its velocity, so mass of B multiplied by velocity of B initial. And in an inelastic collision, these two guys are going to stick together and go off at some other velocity. So this is going to now be mass of A plus mass of B multiplied by a shared velocity, velocity 2. So now it's a simple matter of saying, okay, well, how fast is that car going? What is this value right here? Well, simply I divide both sides by the total mass of the system, and I get an expression for velocity 2 being related to the momentum of the A guy initially, so mass of A, velocity of A1, plus mass of B, velocity of B initial, divided by the sum of the masses of those two guys, mass A plus mass B. And I just have to be very, very, very careful to remember that my velocity of B1 is going to be negative when I put that guy in there. The velocity of A1 is going to be in the positive direction, and the math will tell me whether I chose V2x being positive or being negative to be right or wrong. If it comes out negative, then it's going in the left direction. So we can go ahead, we can plug all those guys in there, and we're going to come up with 0.5 meters per second. So a ballistic pendulum is a perfect example of an inelastic collision with kind of a cool application. I'm going to work one in the work problems. I'd also highly recommend you follow the example illustrated right here and make sure you understand that. But with this type of setup, we have a bullet coming in at some velocity to a mass, at a block of wood that is at rest. There's going to be an inelastic collision, a totally inelastic collision. We would still write the momentum beforehand is going to be equal to the momentum afterwards, just like we did on the last slide. And then immediately after the collision, the bullet's now lodged in there. We can calculate what the momentum is, but now it's going to swing upwards. In this particular case, now what we can do is we can use energy conservation to figure out how high the swing is going to go. We can say that the kinetic energy of the block plus the wood is all going to go into the potential energy at the very tippy top of the swing. We can solve for the velocity using conservation of momentum. Now we can solve for the kinetic energy, and if we know all the kinetic energy is transformed into potential energy, now we know how high this block must move. When we're talking about elastic collisions, we also need to think about how inertia or mass is going to affect the collision. If you've ever played pool and you're actually somewhat good at it, you might consider a collision between two balls where they have equal mass. Here we have ball A running into ball B and it has some velocity. If the collision is perfectly elastic, then all of A's momentum and all of A's kinetic energy are transferred directly to B, assuming that they have the same mass, and B is going to shoot off with A's initial velocity, and A is going to come to a complete stop. However, if we're talking about objects that have different masses, for example, this ping pong ball that is going to run into the bowling ball, it's going to have some initial velocity, it's going to bounce off of the bowling ball, and we know that the bowling ball doesn't really want to move, it's very massive, it has a lot of inertia, so the ping pong ball is going to bounce back in the negative direction and just give the bowling ball just a tiny little bit of velocity. If we consider the bowling ball striking a ping pong ball, then we know that the ping pong ball doesn't have a lot of mass, it's not going to resist that change in momentum very well. So the bowling ball is simply going to bowl over the ping pong ball and give it actually a fairly large velocity with relatively little change to its velocity. So I've mentioned in elastic collisions that both energy and momentum are conserved, and that actually buys us something. Following example 8.10 here, we will always say for any collision that the momentum beforehand is equal to the momentum after, and we're all getting to be experts at writing what the momentum before and the momentum afterwards are, yes? We can also say in the elastic case that the kinetic energy beforehand must be equal to the kinetic energy after. What that does is, if we know all the velocities and masses beforehand, we can now solve for not one but both of the velocities, va2x and vb2x, here using both kinetic energy conservation and momentum conservation. We now have two equations that describe our velocities, therefore we can solve for two unknowns. And I don't have space to do example 8.10 on this slide here. I highly recommend that you take a look at that example and figure out what's going on. But it turns out in general that we can write the velocity v2x minus va2x to be equal to the negative v1x minus va1x for the case of elastic collisions only. So now we would come up with this guy using kinetic energy conservation, and then plug one of those velocities up into our momentum conservation, and then solve for one of the two velocities, come back down to this equation right here and solve for the other velocity. I will highlight that this only applies to elastic collisions. If you simply root through the book for equations and you try to apply this equation to an elastic collision, then you will make a very bad mistake and solve the problem completely, totally wrong. Here I'll genuflect in the direction of two-dimensional elastic collisions, remembering that we're always going to write the momentum beforehand in the x direction is going to be equal to the momentum afterwards in the x direction. The same thing for the y direction, we're going to write momentum beforehand in the y direction is equal to the momentum after in the y direction. However, energy does not have direction associated with it, so we're still only going to have one kinetic energy equation. Kinetic energy before has got to be equal to the kinetic energy afterwards, and we proceed to solve the problem following example 8.12. So let's shift gears a little bit and start to talk about the center of mass. Up until this point, we've been talking about boxes going up ramps and balls and so on and so forth, and we've never really considered the size of the object that we are pushing up the ramp. However, what we've essentially been doing is we've been, knowing it or not, using the object's center of mass to describe its motion. The definition of the center of mass is the point where you can consider all of the object's mass to be at. You can consider it to be a balancing point, if you will. I mean, if we had a meter stick like that, then the center of mass is going to be where you balance it right there, probably about the middle of it. And then if you could balance it on the end, then it's going to be simply right there in the middle of it. Cubes and spheres and cylinders, all that stuff, it's going to appear in the middle of it. So we have in effect been treating the center of mass to be the point that we're that the pointer motion has been about up until this point. I'll also say that if an object has an axis of symmetry, like a disk or a donut, then the center of mass is always going to lie on that axis of symmetry, although it doesn't necessarily have to lie within that object. For example, if you wanted to balance a donut, intuitively you would say, I would have to balance it from the dead middle of the donut. To calculate these mathematically, it's a fairly simple formula. We would say that the position of our center of mass is going to be an object's mass multiplied by its x position plus a second mass, mass 2 multiplied by the second x position plus the third mass multiplied by an object's third x position, divided by mass 1 plus mass 2 plus mass 3. I've simply sketched out a 3-body problem. In general, it's going to be the sum of an object's mass multiplied by its distance away from the point that you're defining to be 0, divided by the total mass of the system. So here I've written it for 3 discrete points. Here that would apply to disks and cylinders and so on and so forth. We can do the same thing for the y direction, where we say that the center of mass in the y direction is going to be the sum of all the masses multiplied by their y position divided by the sum of the masses. If you're not totally convinced of the utility of knowing an object's center of mass, recall that the object's going to behave as if all the mass was concentrated at the center of mass. So if we take a wrench and we give it some velocity from the bottom of the page to the top of the page, but now in addition to giving it translational motion, up and down motion, now we're also going to give it some rotational motion. We can see that the book has, kindly for us picked out where the center of mass of this wrench would be. It's going to be nearer to the large massive head of the wrench than the far end of it. We can see that the center of mass of this wrench is moving with a constant velocity covering equal distances and equal amounts of times, regardless of whether it's rotating or not. Also, we're tying this back into the momentum that I was talking about earlier. What we would do is we would say that the total momentum of a system is going to be equal to the mass of the system multiplied by the velocity of the center of mass. So again, for this wrench, I pretend like all of the mass is concentrated down at the center of mass, and I can apply my momentum equations to the center of mass of the system. Just a really quick calculation of center of mass considering a tug of war on frictionless ice, and I'm defining here my 0 point to be the coffee mug. So here I have James weighing 90 kilograms, and his distance, so position of James, is going to be negative 10 meters. And over here, on this side, I'm going to have Raymond, and he's going to have a position of 10 meters. I'm asking what is the center of mass of this tug-of-war system, and the rope is, of course, massless. I simply say that the position of the center of mass, relative to the coffee cup, mind you, is going to be the mass of James multiplied by the distance of James, so mass of James multiplied by the distance of James, plus the mass of Raymond multiplied by the distance of Raymond, divided by the mass of the entire system, James plus Raymond. I go ahead and I say, so this is going to be 90 kilograms multiplied by negative 10, plus Raymond's 60 kilograms in his position of 10 meters, and then the mass of the system, which is going to be 150 kilograms. And I'm going to come up with the center of mass to be equal to -2 meters, the position of the center of mass. That intuitively makes sense to you because you know that Raymond is more massive, or you know that James is more massive than Raymond. So if you wanted to balance this system, you know that it's going to be on the negative side of the coffee cup. So the last thing I want to talk about is rocket propulsion. Rockets are propelled simply using conservation of momentum. We're going to say that a rocket is initially at rest, and so it's going to have a momentum beforehand equal to 0, and then afterwards it's going to have a mass of the rocket traveling at some velocity, and it's going to have a mass of the gas traveling at some velocity. So saying momentum beforehand is equal to the momentum afterwards, we can simply say that the mass of the rocket multiplied by the velocity of the rocket is going to be equal to the mass of the gas multiplied by the velocity of the gas. I forgot my negative sign here. The negative sign means that they're going in opposite directions, and obviously gas doesn't weigh a whole awful lot, so it must be traveling at a very, 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 very large velocity in order to propel this very massive rocket, which is pushed off in the opposite direction at a much smaller velocity than the velocity of the gas. Now, this is the simplest possible case. In the real world, we actually have to take into account the fact that the rocket is losing mass. It is becoming more and more lighter, and so actually it is increasing its velocity. So as the rocket loses fuel, that dm is a change in fuel, the rocket is correspondingly increasing its velocity. So when we write our momentum equations, we take all that into account, and we do have to do a little bit of calculus to do that.